All of the following things have something in common: a cloud, a rubber tire, a piece of paper, some plaster, some fresh paint. These totally different things are all examples of colloids, materials in the colloidal state. The colloidal state is only one type of dispersion, in which small particles of one material are scattered or dispersed throughout a second material. One way to define a colloid is by comparison with other dispersions. If we mix some copper sulfate crystals in water, they dissolve. They separate into particles of molecular or ionic size. The chemist calls this kind of dispersion a true solution. In a solution, the particles will not settle out. Now we'll make another kind of dispersion. We'll mix white, coarse sand in the water. It doesn't dissolve, but settles out in a short time. We call this kind of dispersion a suspension. But if a material is ground until the particles are very fine, like this white clay, then it neither dissolves nor settles out. This condition is called a colloidal dispersion, which is somewhere between a solution and a suspension. To learn more about the relative sizes of particles that form a colloidal dispersion, let's see what we can learn by filtering the solution, the colloid, and the suspension. We find that the solution comes through the filter paper. The colloidal dispersion, too, comes through the filter. But the coarser matter of the suspension, the sand in the water, does not come through the filter. Evidently, the suspension contains the largest particles of our three examples. Both the solution and the colloidal dispersion pass through the filter. Are colloidal particles, then, as small as the molecular particles of solutions? Perhaps we can answer the question with this experiment. Let's mix a salt solution and a colloidal dispersion of starch. We'll place the mixture in a bag made of a semi-permeable membrane. We suspend the bag in water. Then we pour in our mixture of a solution and a colloid. Next, we are going to test to see what passed through the membrane into the water. When iodine, a reagent used to test for starch, is added to the bag, it turns blue, showing that starch is still in the bag. Iodine in the surrounding water shows no blue reaction, so starch didn't pass through the membrane. Silver nitrate is a reagent used to test for the chloride ion of salt. It does show the presence of salt in the water, so the salt, in solution, passed through the membrane. The starch, in the colloidal state, did not. Colloidal particles, then, must be larger than the molecular-sized particles of solutions. And so particles in a colloidal dispersion are between the smaller size of particles in solutions and the larger particles in suspensions. We have other indications of the relative size of colloidal particles. If we shine a strong light beam through a solution, we can scarcely see the path of the beam. In a colloidal dispersion, the path of the beam is readily visible, reflected by the larger particles of the colloid. This is called the Tyndall effect. We can use the effect of light in another demonstration. We can't see colloidal particles under a microscope, but a light beam, shining sideways through a drop of colloidal material, reveals tiny points of light reflected by the particles. We notice, too, that these points are in constant, irregular movement. This is called Brownian movement. The reason colloidal particles showed Brownian movement is that smaller particles, molecules, were constantly striking them. Something like this. causing them to remain in suspension. Colloidal and other particles are measured in extremely small units, millimicrons. A millimicron is 1/1,000,000th of a millimeter, or 1/25 millionth of an inch. Particles about 250 millimicrons or more in diameter show the properties of a suspension. Particles 1 millimicron or less are molecular and show the properties of a solution. Between the two, say between 1 and 100 millimicrons, are colloidal particles. Here's another way we can get some idea of the relative size of colloidal particles. Here are thousands of grains of sand. If we were to take just a single grain of sand and look at it under magnification, we'd see this. Within this one grain, we could put hundreds of colloidal particles. So far, we've discussed colloids, which were solid particles dispersed in liquids. But as we saw earlier, there are other types of colloids. Let's see the different ways that matter can form colloidal dispersions. We know that matter can exist in 3 states: as solids, liquids, or gases. Any one state can be dispersed in any other, so there are 9 possible pairs of dispersions. Solids dispersed in solids, in liquids, in gases. Liquids in solids, in liquids, and in gases. Gases in solids, in liquids, and in gases. Let's see examples of each pair of dispersions. Carbon black particles dispersed in the rubber of a tire are an example of a solid dispersed in a solid. Paint is an example of a solid in a liquid. A solid in a gas is smoke, tiny solid particles dispersed in air. Butter is a liquid in a solid, that is, water in butter fat. Many hand lotions are liquids in liquids, such as oils in water. Some very fine sprays, such as aerosols, are liquids dispersed in gases, such as oil in air. Plaster of Paris is a gas, air, dispersed in a solid, calcium sulfate. When you whip cream, you're making a colloidal dispersion of a gas, air, in a liquid, cream. What about a gas dispersed in a gas? Here we're going to mix chlorine and bromine. In the mixing flask, the 2 gases are forming a dispersion. But we should remember that this is a mixture of molecular-sized particles, and that defines a solution, not a colloid. Therefore, a mixture of 2 gases is not a colloidal dispersion. So we have then 8 possible combinations of matter in different states that may produce colloidal dispersions. We saw some of the 8 combinations that can give us a variety of colloids, but they are all made in 2 principal ways. We know that particles too fine to settle out of their dispersing medium will form a colloid. So one general way to make a colloidal dispersion is to break matter down to particles of colloidal size. A great many colloids are made by mechanical means. In this mill, coarse solid particles are ground down to colloidal size small enough to be dispersed thoroughly in a liquid medium. This mill grinds pigments mixed with an oil base to form a colloidal paint. Sometimes, in dispersing one liquid in another, we run into difficulty. You've probably seen vinegar and salad oil mixed together. It is difficult to break up the oil droplets finely enough to stay suspended. They tend to merge together, to coalesce to larger size, and come out of suspension. To make them stay suspended, we need an emulsifier. In this case, we're going to use egg yolk as our emulsifier. When we add the emulsifier to the 2 liquids, vinegar and oil, we find that the oil will stay in suspension. The emulsifier forms a protective film around the oil droplets, preventing them from coalescing into larger than colloidal size. This particular emulsion, or colloidal dispersion of two liquids, is a familiar one. It's mayonnaise, oil and vinegar emulsified with egg yolk. Just as we can prepare colloidal dispersions by grinding matter down to extremely fine size, we can make colloidal particles in a second way. Instead of breaking down particles, we can also build them up. In a solution, we can coagulate or build up molecular-sized particles to larger colloidal-sized particles. When we add ferric chloride to boiling water, for instance, reddish hydrated ferric oxide. This colloidal dispersion was made chemically by combining molecular-sized particles to form the larger colloidal-sized particles. The colloidal particles of the same substance have the same electrical charges. In this case, they are the positive charges. Since the positively charged particles repel each other, they stay separated in suspension. However, if we neutralize the positive charges, the particles could become larger than colloidal size and precipitate out. In other words, having made a colloid chemically, we can destroy it chemically. One way to do this is to add an electrolyte to the colloidal dispersion. Negatively charged ions in this electrolyte will be adsorbed by the colloidal particles and neutralize their charges. Watch what happens as we neutralize the positive charges on the colloidal particles. As the particles are neutralized, they clump together or coalesce and begin to precipitate out. So it is possible to destroy a colloid chemically. Later we'll see what value this has. Another way to destroy a colloid is by use of a strong electric field which we can apply in this tube. We introduce smoke, which is a colloid, with electrically charged particles. A current through the wire neutralizes the charges on the smoke particles. They drop out of suspension. It's obvious what use this process might have. The problem of industrial smoke abatement is being solved by the principle we just saw, by electrical precipitation of the colloid, which is smoke. But this is only one way in which an understanding of colloids is useful to us. For instance, tanning leather involves precipitating colloids chemically. The hides, which are made into our shoes and other leather goods, are largely protein colloids. Liquid latex, another colloid, is coagulated in the process of making rubber. In another phase of rubber manufacture, liquid latex is precipitated electrically onto rubber forms. Once more, precipitation of a colloid. A component of milk, casein, can be precipitated chemically by acids or by an enzyme called rennet. The precipitated casein can be dried, as we see here. Casein has important industrial uses. Much of the casein made today is used as a coating for paper to improve the quality. A more recent and growing use of casein is in the preparation of high-protein foods, such as this cereal. Edible casein is also added to certain kinds of ice cream. Casein is used as a binding medium for some of our household paints. We constantly use the products and principles of colloidal dispersions in hundreds of practical ways. Soaps and detergents, for instance, are emulsifiers. Washing involves forming an emulsion of oily dirt particles and water, an emulsion that carries the dirt off the skin. Many of our foods are colloids. Homogenized milk is milk in which the fat particles have been broken down to colloidal size so that the cream doesn't separate out. The dyes that color our fabrics owe much of their tinting power to colloidal properties. These are only a few of the thousands of ways we put to use our knowledge of materials in the colloidal state.